Но я могу опять написать Гоша. Все, что я могу сделать. Ну, как бы...
Вот началась, да, действительно задержка полчаса. Может?
Так, хорошо, ладно, звук есть, звук. Теперь что-то слышно?
Нет, ну там даже слышно нас, по-моему, значит, я думаю, вас точно.
Хорошо, окей, ладно. Okay, so let us start. Last time we learned how to construct a toric variety from a fan. But I think that today we will not use it very much. So last time we had a fan, which is a collection of cones. And now our question is if we have a toric variety, so a quasi-projective variety with the torus action, how can we recover its fan structure? Okay, so our first topic for today is limits of torus actions. First of all, we take one parameter subgroups. Do you want an example? Maybe. Yes. Okay. So first of all, I write some statements and then we have an example. First of all, what is an action? So let our torus, which we denote by Tn, meaning that it has dimension same as dimension of n, Tn act. First, let x be affine. I mean that Tn is an open subset of x. So a morphism which exists in this case, Tn times x to x. It corresponds to the map of algebra of regular functions in the reverse side. It will be so it will be C of our semigroup S if we suppose that x is constructed via a semigroup S. Okay? In this case, we should map CS to Cm times Cs. Cm is the algebra of regular functions on the torus, and we tensor it over Cs. So what does it mean? Yeah, I say x toric, Tn acts on x and is an open subset. So what is this map? We can write it exactly. If we have a character here. Any question? So it is generated by characters. So chi m will map to chi m viewed as an element of Cm, tensor chi m viewed as an element of Cs. So if you want to calculate a character, its value is multiplied by the value on the torus which acts and on the value of the point. Yes. So on the first lecture, we had different definitions of an affine toric variety. First of all, we say that if S is a finitely generated semigroup in some lattice M. This was one of the initial constructions. Later we took sigma check in M, a rational polyhedral cone. In this case, S is the semigroup which figures here is just the sigma check intersected with M. If you want, I write the same here instead of S. Okay.
Yes, where's the action? So it's like, what
Where?
if we have another action? This will be the same.
No, I mean, if we have a toric variety, it means that we have a fixed open subvariety isomorphic to an algebraic torus, such that the multiplication of on the torus by itself extends to a regular action on X.
Yes.
It means that if you have coordinates on X and you have coordinates on the torus, the result of the multiplication is given by polynomials in both sets of variables. Just both are affine algebraic varieties. Here is the action. So the action is how do we multiply coordinates on X by some elements of the torus. And the next is if we take a character, maybe it is a regular, maybe it is a coordinate function on X. You just see that if it's multiplied by some element of torus and another point of X, you calculate the value of this character. It is just the product of this character on the torus and of this character on the variety.
Yeah, that makes sense. Okay.
So today we will have many notation. I hope it will be more or less clear. I think that there will be no very deep statements today, but lots of notation to work with the limit points. Okay, so the lemma is that if we start with a cone of full dimension, then then the torus action has the unique fixed point. So lemma if I write it so if X is spec, I better write it in the dual space. If X is spec CS, so it just means that the algebra of regular functions is CS. Then the torus action has a fixed point if and only if in the dual space it will be pointed. If and only if the cone corresponding is pointed, which is equivalent to the fact that the only invertible element of our semigroup of our semigroup is 0. If this object in M is pointed, then the cone sigma in N is of full dimension. Yes.
The only
Invertible element of our semigroup is 0. And we can say if it corresponds to, I can write sigma check is pointed. Okay? Ну, там нету подпространств. It contains no subspaces. Okay. And in this case, we can say what is the fixed point of this action. So for this, we need to say that in this algebra, in this, each point can be viewed as a semigroup homomorphism to C. So each point of X is a semigroup homomorphism from S to C. Using this, we can say that the unique fixed point is given by so we say that it is pointed if M equals 0, it maps to 1, and if M is non-zero, it maps to 0. So I can draw the vertex maps to 1, and all the other elements, they map to 0. All these map to 0. Okay?
how each point of X gives homomorphism?
Each point of X, for example, it has coordinate functions. And it has another functions. The algebra of regular functions on X is generated by monomials chi m. So if you take different monomials, their values should correspond to each other. Two monomials, if the product of two monomials is a third monomial, then their value must multiply. So, for example, if you have coordinate functions here, you take their values, and then you say what are the values of all the other functions. Or just say that an affine variety, a point of an affine algebraic variety, is a morphism from your field of functions to the ground field.
Yeah,
That's exactly this morphism. We just said that the algebra of regular functions is generated by monomials. Yes. So this is the unique fixed point, and we can check that it is true. Proszę. Why? We can write using this formula. Okay. So let us prove this. Let a point X correspond to the semigroup homomorphism I just give the formal proof. If you don't like it, you can translate it into some coordinates and some more geometric proof. But the essence will be the same. Let's do the semigroup homomorphism. I denoted by gamma, which goes from S to the complex numbers. Okay? It means that for each, we know that X is a fixed point. If X is a fixed point, then how do we act? So for each m, for each monomial m, we write the action. It is chi m of t multiplied by gamma m. Gamma is from S to C, and by this formula we just multiply these values. Okay?
So he writes an action.
What if we act by chi m from the torus on our point which is fixed on our variety x, and write what is that our point is fixed. So it is gamma m. I mean, each point is a homomorphism from the algebra of functions.
So we have like points on x, and you see this action, and
Yes.
Consider it as an action on semigroup homomorphisms.
Yes, yes. So if chi m acts on x, then it acts on the algebra of functions. It acts by this formula. So the element of torus acts by chi m, and then the function here, its value is gamma m.
What is t?
Uh,
Element of torus?
yes. Yes, and so if it is true for each m, we can understand what happens. So if m equals 0, then it satisfies, because chi 0 is always equal to 1, and we have gamma of 0 equals gamma of 0. And if m is a non-zero element of lattice m, then there exists t such that chi m of t is not equal to 1. Yes, and then it implies that gamma m equals 0. So once more, m is an element of our lattice m, and if it is not 0, it corresponds to some character of our torus, and then there exists some t such that it doesn't equal to 1, and we get that gamma m equals 0.
So what if gamma of 0 equals not 1? Just another thing. Anything.
One moment. We know that gamma is a semigroup homomorphism. So first of all, we have that if this point exists, it corresponds to this object. Okay, gamma 0 equals gamma 0.
So gamma 0 is either 0 or 1.
Yes.
Yeah, so
What if everything equals 0? I think it contradicts the definition of semigroup homomorphisms, because if everything goes to 0, it's not interesting. We should assume that
But still it holds the case,
it.
the constant.
Sorry?
I mean, still it holds the case. I mean, we can assume that it is a constant when it goes to 0.
No, I mean, if everything goes to 0,
Will not be a problem.
I think that yes, it will be a problem, because we have a constant function which equals 1 on our variety, and it cannot map to 0.
Yeah, but what is the semigroup structure of C?
Why? The semigroup structure of C, you have one coordinate.
Yes. So it's like, what's we using plus or multiply as an?
If we have a semigroup structure, we multiply. But we have function which is constant 1.
Yes.
It corresponds to chi0. So it will go to 1.
Everything goes to 1.
So gamma 0 equals 0 doesn't work, because it maps the constant function to 0. It is on each affine variety you have a constant function which equals to 0.
Yes.
If it maps, constant function which equals to 1. If we consider the map of semigroups, it's not interesting to map everything to 0. It makes no sense to send the constant 1 to 0. It doesn't correspond to points. Okay. Let me write here that.
When you say it's not interesting, it's
No.
not I don't.
Once more, it doesn't correspond to points of our variety, because in the algebra of functions, it doesn't correspond to coordinate functions. It is just the constant functions in our algebra of functions. C of A1. Okay. If we consider maps to complex numbers, if we consider points in A1, you will not send the constant function to 0. Okay, I'll let me answer you later. Okay?
No, actually, I think I understand this, but I'm not really sure.
Okay. Let's discuss this point later. I mean, we.
So everything here, so C, so it should be a varieties of C algebras. So I think that's why one should be preserved.
Yeah, one should be preserved.
Yeah, that's a good explanation. Okay, one should be preserved. So chi 0 is not 0, and then chi 0 equals to 1. So there is a unique morphism which works in this case.
Where did we use that?
One moment. If S is not pointed, this is not a semigroup homomorphism if S is not pointed, there exists M such that M in S and minus M in S. In both definitions, you can find such M in both definitions. And then, so chi M chi minus M equals chi 0. But you will have 0 times 0 equals 1, which is a contradiction. So in this case, sigma, so S needs to be pointed. And conversely, if S is pointed, then this gives us a semigroup homomorphism. This gives us a semigroup homomorphism, and such a point exists. If you define it in this way, conversely, if S is pointed, then we define gamma of 0 equals 1, gamma of M equals 0, and it is correct because we don't have such a situation. Everything which has a non-zero M will go to 0. So this lemma is proved. Okay? So this works for sigma. If we start with sigma of full dimension, then if dimension sigma is dimension nr, then sigma is pointed, and the affine toric variety x sigma has a unique fixed point. Okay. What next? Let us consider one example. What can be what one parameter subgroups can we have in our torus, and what will be their limit points? So our aim will be to recover the fan structure from the torus action, and T orbits on P2. Suppose that we take a point A, B in Z, and then we have a point 1 TA TB in Tn. Okay? Then we have what if we act on a point with coordinates x0, x1, x2, and then if t tends to 0.
Why is there such point in Tn?
I mean, we have P2. The torus in P2 is when all the three coordinates are not zero. And I say that each point of torus can be represented in a way where we have one here. I just say, suppose that we took a point AB from the lattice N. The lattice N was the lattice of one parameter subgroups of our torus. Okay? So for each element of the lattice of one parameter subgroups, we consider this one parameter subgroup. And now we check whether this action has a limit point. Okay? So we draw it in the lattice N. Does it have a limit? This will be, this is N. When, so what is the limit? What is the limit for some fixed A and B? Okay? If A and B are positive, then you see that it will be the limit point 1, 0, 0. So in this region, it will be 1, 0, 0. So first we consider this example, and then we try to formulate a general statement in which we will use this lemma. So A positive and B positive. What cases can we consider? If A equals 0 and B is positive, it will be 1, 1, 0. Okay? If A and B equals 0, this will be 1, 1, 1. Then if B equals 0, this will be 1, 0, 1. And what else? We have the case when A and B are negative and equal. If they're negative and equal, then it will be T minus A 1, 1. So on this line, we have 0, 1, 1. Okay? And we have two more fixed points. In this region, we have, so we draw this, and we draw this. In this region, what do we have? We have if so B is negative, it goes to 0. It will be, so
I think one of them is negative and one of them is positive.
no, I wanted this case. So I should get two more fixed points in this case and in this segment and in this segment.
Yes, I think at that segment it will be A is greater than 0 and B is less than 0.
Sorry?
A is greater than 0, A is positive and B is negative.
No, it is not what I want. Okay, let us divide by, if we have that B is negative here, no, not A is negative, A is negative. Let us multiply by, let us divide by TA. It will be, the result will be T minus A maps to 1, maps to T B minus A. Okay? Here B minus A is positive and minus A is positive. So if T tends to 0, it will be, the limit point will be 0, 1, 0. And in the similar way, here we have that B is negative and A minus B is positive. So it will be, the limit point will be, it will be 0, 0, 1. Okay? So we just look at the lattice of one parameter subgroups, and we see that we have 3 fixed points, and we have limit points which depend on the cones of the fan. I recall that a fan is a collection of cones, such that each face of each cone also is listed in our fan, and that 2 cones, if they intersect, the intersection is also a cone in our fan.
What is the point 1, 1, 1? What represents the
It is
smallest cone?
it is 0 in the lattice n. It is the it is the limit point for this case. It is okay. Okay. We want to say now that there is a correspondence between a sigma, a cone in our fan, and T orbits. So we want to prove that for, if we take U, U in N, then the limit lambda U T when T tends to 0 belongs to the orbit O for each U from the relative interior of sigma. This is our aim.
What is the right way this whole?
I should maybe write. We had this on the very first lecture. What are the torus orbits here? It depends on zeros. There is one orbit.
It's already
Not quite. So there is O1, which is non-zero. Okay. This will correspond to this point. Then we will have orbits, for example, O2, O3, O4, where 1 over xi equals 0. And you see that in this case, only one limit point belongs to each orbit. So one of them contains this point, one of them contains this point, and one of them contains this point. And 3 last orbits which consist of 1 point. 3 fixed points. Which coincide with the corresponding limit points. Okay. So now let us generalize the fact about points and semi-group homomorphisms for cones which are not necessarily of a full dimension.
What is that making? What is it Chi?
This is this is one parameter subgroup. Chi usually stands for the character of the torus, and this is a one parameter subgroup. Okay, so now sigma is not necessarily pointed. No, not necessarily of a full dimension. So what do we have? A point in the corresponding defined toric variety U sigma can be defined by the obvious way, but by the only possible way. If we take M from sigma check intersected with M, we should map it maps to the maximal linear subspace here is sigma orthogonal. So if M belongs to sigma orthogonal intersected with M, then 1 and 0 otherwise. Okay, so we denote it by gamma sigma, and it is the distinguished point corresponding to sigma. Okay, it is clearly it is fixed by our torus if and only if sigma is a full dimension. As we see here, if sigma is a full dimension, it is a fixed point, and if the dimension is lower, then there is a torus which acts. Okay, and one important property is that if tau is a phase of sigma, then the distinguished point gamma tau belongs to the affine open subset U sigma. Why? Because on the orthogonals we have that sigma orthogonal is a subspace in tau orthogonal. And so what is gamma tau? It is a map from tau check intersected with M. And we needed to be one on this. So, a map which vanishes, which is one here, it will be a semigroup map for this semigroup. I say that each point of U sigma is a semigroup map from this to C. Okay? And if we have a gamma tau, it is a map which equals 1 on tau orthogonal and 0 on all the other points. Since tau orthogonal is a subset of sigma orthogonal is a subset of tau orthogonal, the corresponding semigroup map will be also a semigroup map here. It will be another map which will have more ones. If it equals 1 on tau orthogonal and 0 otherwise. This is also a point of U sigma. Points of U sigma is the semigroup homomorphism from sigma check to C. There is a tau orthogonal which maps to 1.
Yeah, but gamma tau is well, it takes any point of tau check which is larger than sigma check.
Yeah, and then we're restricted to
sigma check.
yes. So we have tau check intersected with M, which is bigger than sigma check intersected with M. Each map from here to C can be restricted to a map from here to C.
Yes.
And we know that it equals 1 on tau orthogonal. Then this will be a correct semigroup map here. So if we know that if sigma check is not pointed, we have the condition that this should not vanish. It doesn't vanish. And it can be extended on all the other generators. So we know that there is a subspace on which it equals 1 and it equals 0 otherwise. It is a well-defined semigroup homomorphism from here to C. Okay. And now let us prove. Can I erase this? I erase this. So now our lemma is that if sigma is a strongly convex cone, and suppose that we take U from N, then U belongs to sigma if and only if and only if the limit when t tends to 0 of the corresponding one parameter subgroup lambda u of t exists in U sigma. Okay, the torus is a subvariety in U sigma, and so either it has a limit or not. And if we take U from the relative interior, if U is taken from the relative interior of sigma, then the corresponding limit is limit of this stuff equals our point gamma sigma. Okay, this is our statement. It is not very difficult. So, if let us prove it. If the limit lambda u of t exists in U sigma, then suppose that we take any character which is a function on U sigma. We have the limit of chi m. It can be a coordinate function of lambda u t. So character is a map to C, and this limit exists in C for all m from sigma check. Okay? For example, we have coordinate functions on our toric variety, which are also some characters. Okay, this limit exists, and we know how to find it. So we have a pairing. It is exactly T. We have the pairing mu exists in C, which means that mu is non-negative. Mu is non-negative for all m. For C check second with m.
I'm not sure that we have this pairing. Have we had this pairing?
Yes, it is given with the torus. If we have the torus, if we fix its representation as C star power n, at this moment we say that all the one parameter subgroups are given by some user from this lattice, and all the characters are given also by monomials. And if we calculate the value of the character on a one parameter subgroup, we just plug the coordinate presentation, and we have T power this pairing. It is just the very, very definition. Okay, so this means that U belongs to sigma check, to sigma. Since we take M from sigma check, then U belongs to sigma. We proved that sigma check is the same as sigma. Okay, and if we take U from the relative interior of sigma, it is equivalent to the fact to then this pairing is positive for each m which is not in the maximum linear subspace. For each m which is in sigma check without sigma orthogonal. Okay? And we will have the map will be, the map in this case will be once when this vanish, the map sigma check intersected with M to C will be t power 0 for M from U orthogonal and 0 otherwise. Sorry? Sorry, sigma orthogonal. I don't write completely. It is sigma orthogonal intersected with the sigma check. With M. Intersected with M and intersected with the sigma check.
Sigma orthogonal already in sigma check?
Yeah, it is in sigma check. Okay. Intersected with M, okay. But we see that if we take U from the relative interior, it is exactly this semigroup homomorphism. Okay. So it is gamma sigma. Okay. So it allows us to reconstruct the torus structure if we know how the torus acts. Okay. And now I think I should write what is our aim and prove some lemmas necessary to prove the aim. So the orbit cone correspondence. Maybe I recall that now we have a fan. And for each cone in this fan, we have several objects. First, we have U sigma for each cone. Then we have the point gamma sigma, and also we can consider the orbit. We write O sigma is the torus applied to the point gamma sigma. Okay, so here we have all the torus and then some smaller subtori. So we have fan delta, and x delta is our variety. So first, there is a bijective correspondence between cones in our fan and T orbits, Tn orbits on X, where we can, on X delta, we map sigma to O sigma. And also we can write that O sigma is isomorphic. It is some torus of smaller dimension, and it is a homomorphic Z sigma orthogonal intersected with M and C star. This means that sigma orthogonal intersected with M is its character lattice. Then if we denote n the dimension of nr, we know that dimension of O sigma equals n minus dimension sigma. In this picture, the dimension of this cone is 0, and the orbit is two-dimensional. It is the whole torus. And for the fixed points, the point, its orbit has dimension 1, and dimension sigma is the maximal possible. Okay, and then why did we need so difficult semigroups? The affine open subset U sigma can be written is the union of orbits for all the faces. Tau is the face of sigma, and we take O tau. And the last is that we can describe the orbit closures. If tau is a face of sigma, is equivalent to the fact that O sigma belongs to the closure of O sigma of O tau, and O tau, the closure of O tau, is the union for all the sigma which contain tau, O sigma. It is in both the classical topology and the Zariski topology. Okay, it is our aim. Let us prove something. First of all, I want to discuss this. So, this is the union of all O sigma.
Why?
Because
Tau is the fan of sigma, right? Sorry, face of sigma.
no, you shouldn't mix up U tau and O tau.
Yeah, tau is the face of sigma.
Let us check here. Tau is the face of sigma. Okay? O tau, the closure of O tau. Let us take this tau and this sigma. O tau, in this case, it is something, 0, something. And O sigma is, in this case, O tau is something, 0, something. And O sigma, this is sigma, it is these points. Okay? If you want to take the closure of O tau, which points do you add?
In the third column. I mean,
You should add this point where we have 1, 0, 0. And you should add 0, 0, 1. So you add this point and you add this point. So this will be, if you take the closure, it will be a toric variety, and you will be able to reconstruct its fan looking at the initial fan.
Okay.
And so this will correspond to a torus here, and all in total this variety will be P1. It will be the one-dimensional torus. No. It will be P1, and you will add this point and this point. Okay.
Orbit of the phase, we can convert it by the orbit.
Sorry?
The orbit of the phase. Tau is the phase, right? Phase of.
Yes.
So we can construct the orbit of the phase by gathering all the phases of the original pole sigma.
Not all. The cones of the fan, which contains.
Which is contained in the.
No. If you take O tau and take its closure, you take bigger cones, which contain tau.
Okay, so the union is over the sigma.
If you want, I write sigma, which contain tau.
Yes, I was thinking of that the union is.
No. No, the union is over sigma. Okay. So now, what is the torus of the orbit? I write that there is a perfect pairing. There is a pairing which in fact comes from the initial pairing. But now we write that it is sigma orthogonal intersected with M times N quotiented by sigma intersected with N. Sigma intersected with N is some sublattice in our lattice N. And we can take the quotient lattice, which sends it to Z. So it is just induced by our initial pairing. And this pairing induces a natural isomorphism it induces so homo Z sigma check intersected with M to cis star with this object this is a lattice. If we tensor it with C, with C star, this is just a torus. This is just a torus with this lattice of one parameter subgroups. Okay. I hope this is more or less clear. Just. We need to construct a pairing between two lattices. Initially, we had a pairing M with N. Okay? Now we have some sigma. I draw this is sigma in N. This is sigma intersected with N. And this is the Gaussian space, N of... I just say that what is sigma orthogonal? It is exactly the characters which vanish on sigma. So we take dual bases, and everything which vanishes here lives here. And if we take a quotient space, it goes to 0. And so what remains is indeed a non-generated pairing.
Okay, then
in the last row,
sigma orthogonal, yeah?
in the last row,
On the left.
on the left,
On the left.
no, because sigma orthogonal lives in M on the left. On the left, yes. Yes, thank you. Thank you very much. And what did we explain? We say that O sigma is a T orbit, and its dimension can be less than the initial dimension. And we say that, in fact, its character lattice is defined here. And the torus which acts can be described in this way. Okay? And now we can say on the semi-group language what is the orbit O sigma. So I think the last lemma for today is that O sigma is exactly the set of such semi-group homomorphisms from sigma check intersected with M to C, such that it is non-zero only for M belong to sigma orthogonal intersected with M. And then we will use this lemma to prove all this stuff. Okay. How do we prove this? Let us take the set of semi-group homomorphisms which are described in this way. This is the set of all gamma from sigma check intersected with M to C, such that they are non-zero only for the elements of sigma orthogonal. Okay? Now we will prove that it is a toric variety, and it will coincide with this one. Okay? So we defined O prime is a specific set of semi-group homomorphisms. Clearly, gamma sigma, which was 1 here and 0 otherwise, it belongs to O prime, and we know that gamma sigma is invariant under the the full torus action, Tn action. Okay?
What? Because gamma sigma is not fixed point. Why it's invariant?
Why it is invariant? That was our homomorphism. One moment. It is 1 here and 0 otherwise. Because if one moment, if we write the torus action, it is written by monomials. Okay? And if you take a pair in here, it will vanish.
Yeah, but I want to prove that sigma is sigma is t multiplied by gamma sigma. If gamma sigma is invariant, t multiplied by gamma sigma is just gamma sigma.
Yeah, you are right. Okay. I mean, okay, O prime is invariant under the T action. Okay, O prime is invariant under Tn action. Okay? This is the set of semigroup homomorphisms, and if we multiply them by something non-zero, it will remain non-zero. Okay? And then we know that sigma orthogonal is the largest subspace, is the maximal subspace of sigma check. Okay? And so sigma orthogonal intersected with M is a subgroup of sigma check intersected with M. So if some each gamma defined here is defines as a subgroup homomorphism from here to C star. H gamma defines a morphism I say to C star because they are invertible.
Gamma from O prime?
Gamma from O prime, yes. From O prime defines a morphism sigma orthogonal intersected with M to C star. So each one has an invertible and it cannot go to 0. And conversely, I should erase something. Conversely, if we take a we take a morphism here, it can be extended to gamma. Conversely, each element of sigma orthogonal intersected with M and C star gives us a gamma. We just say that it coincides with this homomorphism on the intersection, and it is 0 on the other points. So we proved that O prime is the same as hom Z sigma orthogonal intersected with M and C star. What else? We can write the exact sequence. Here we write n quotiented by sigma sigma intersected with n, then n, then and 0. Okay, in this here we mean the Z lattice. Okay, if we write this exact sequence, we can tensor it with C star, and we obtain that in fact T, the initial torus T, maps to T which corresponds to sigma intersected with N, and then it maps to and it no, what this quotient. Okay, I just want to obtain that the corresponding tori, what we get, the torus of this stuff is this stuff tensored by C, tensored by C star. It is in fact the homomorphisms of what we have sigma orthogonal intersected with M and C star. Okay, and we have that all the bijections are compatible with the torus action, and we have that since we have gamma sigma belongs to O prime, and the torus which acts it is a quotient of the initial torus, then we get that, and we know that O prime is T invariant. So we get that O prime will coincide with the orbit T n gamma sigma, which is by definition O sigma. Okay, we are more or less done.
Yeah, but the last part.
Yes.
How you get this isomorphism?
I just
This isomorphism?
this is yes, this is the lattice generated by the intersection with the sigma.
Okay.
It is just
Yeah, about this short exact sequence, isn't it should be reversed?
it yes, it should be reversed. Yeah, and then it will work. We have here the sublattice n intersected with sigma, then it maps to n, yes, and then we take n quotiented by intersected with the sigma. Yeah, now we tensor it by C star, and we get that this is exactly the hom Z of this stuff. We had it here.
Yeah, okay. And what's the last part?
The last part.
From this?
Yeah. what do we know? We have the T action, which acts both on O sigma and on O prime. And we know that, in fact, O prime is, in fact, this torus. And so we have that that gamma is a point of O prime, that the T orbit of this point contains O prime, but on the other hand, the T orbit of this point coincides with O sigma. So one T orbit cannot contain more than one T orbit, and it will coincide with O prime. We wrote exactly the torus which gives us O prime.
So
We just say that O prime is the set of semigroup homomorphisms.
yes, we didn't know that this is T orbit.
But all this stuff is T invariant.
Okay.
And we know that O sigma is, O prime is T invariant, and on the other hand, it inevitably contains the torus given by this one.
Yes.
Just by construction, each homomorphism here gives us a semigroup homomorphism.
Yes.
And so O prime, on one hand, it is a collection of big T orbits, and on the other hand, it contains an orbit of it is an orbit of a smaller torus. So it is one orbit.
This I didn't catch. So
Yeah. So we have two tori which act. One of them, so we know that O prime is in fact this torus orbit. This is a torus, and O prime, it is its orbit. But we also know that this,
why? Why do we know?
oh, we say that O prime is the set of homomorphisms which satisfy some conditions.
Yes.
So each homomorphism from here
Yes.
gives us a gamma.
Yeah, this equality I don't have. A
Yeah.
problem, but you say
Yes.
that the torus that we have on the right
Mhm.
have orbit that we have on the left. Then I don't catch it.
I say that, so we have here that this is a torus which is a quotient of the bigger torus,
Yes.
which means that the bigger torus acts with some kernel. And the part which efficiently acts there is exactly our O prime.
So the bigger torus
Yes,
acts on
the set O prime. The set O prime is the invariant under the action of the big torus.
yes.
And then there is some kernel which lives here.
Yes.
And all the other stuff acts there. So O prime is isomorphic to this set.
Yes.
This is the torus.
Okay.
On the other hand,
Why is this the torus?
this is the torus just by construction. It is the set of characters of the torus.
Yes, the set of characters.
And this is the torus. This is the torus which acts. I mean, this splits O prime is invariant under the action of the big torus. Just we said that if we multiply homomorphism by something non-zero, it remains non-zero.
Okay. Yeah, that's true.
So it will split into several t orbits.
Okay.
If it is not one t orbit, it will split into several t orbits. On the other hand, we have the smaller torus which acts, and we said that each element here gives us a gamma.
Yes.
So this set coincides with this set.
Yes.
And so the torus which in fact acts there is given here. Okay?
Why? So I understand that O prime is equal to this one. It's isomorphic to the n quotient by sigma intersect with n tensor with
Yes.
okay.
But the torus acts transitively on O prime.
Yes, torus Tn.
The torus Tn acts transitively on it.
Transitively.
Yes.
Why?
Because if we have two homomorphisms from of this kind, then there is an element of the bigger torus which modifies one to another.
Why?
Just because it is an element of which space? We take here some values. Just we have some non-zero values which we prescribe on this space. So we take these values and we map one element gamma to another element gamma. We just have a homomorphism to C. It has a basis. It had some values on this basis, and we need another values. We just take the quotient, we take the corresponding morphism, and we are done.
Okay, yeah, annex transitively, I believe, okay.
So it cannot split into several orbits of this kind.
Yeah, that's true.
So it coincides with it.
I think a torus section is transitive.
No. In this case, we have a torus action on a bigger variety which is not transitive. But in fact, here we take a torus action on some orbit. Each action is transitive on its orbit. That's what we explain here. Okay. And so that's all for today. And next time we will prove all this stuff. Orbit correspondence, yeah. Okay, thank you.
большой угол, да?
Да просто возле сам. Не, угол с предположением, что он рациональный. Мне кажется, там ты хочешь такое сделать, да? Типа говорить, вот здесь подруга такая характерная, да? Вполне бесконечный набор, здесь, да? Разные. И возьмем угол, которого вот здесь туда придумали.
Да, это много. А ну и логарифмический. Что, какой угол?
Вот, угол между вот этим вектором, который не единичный, который 0,1, да?
Да, там все на поверхности, то есть там
Да,
все моменты.
это важно.
Да, точно.
Да. А этот ну какой?
Да.
Который порождает. Между ними есть углы.
Да,
возьмем такой, которого не больше. Потому что как не складывал, здесь оно по-любому не залезло в прямую.
Да.
А тут по-любому из-за того, что вот это рациональная будет 5 больше.
Ну да, у меня буквально такое же утверждение, только оно вот написано вот таким вот языком.
А каким?
Нет, просто у меня там написано, ну вот возьмем, значит, бета равная нулю, тогда там можно все задать одним. Потом возьмем бета равная единице, там можно все задать конечным количеством. И так вот я накручиваю, и в какой-то момент из того, что иррационально, у нас всегда должна добавляться еще одна порождающая. Вот у меня такой, то есть это в принципе одно и то же, просто это какой-то рассказ про кузнечиков на окружности, вот, вместо того, чтобы реально вот так сделать. Да, хорошо.
Чтобы я сначала выбрал, я сначала взял самое минимальное расстояние до оси.
До оси. Ну это плюс-минус почти то же самое.
Не совсем там нюанс. Короче, надо ставку шубу.
Ну да, кстати, там действительно больше чего-то сломаться. Да, ну конечно, так нехорошо.
Ну да. Ладно, правильно.
Еще раз, удачи. Ну, почему у нас ТН
Нет, я выпал. Первый половине не знаю, семинар, где
что-то было
негативный фактор конструкции.
Ну, посмотрим, что он расскажет.
Егор. Это правда. So where are you from?
I'm from India.
Oh, wow. Far away? Well, no.
Not so far away.
Yeah. This is the same continent.
Yeah.
So sorry, my English. Do you study on math faculty right now? Or
Yeah,
it's exchange program?
No, not faculty.
Oh, wow. Awesome. Which course?
It's a magistratura.
Oh, the same.
Okay. So you are in the first course or second course?
First.
Oh, okay. That's nice. I'm also in the first course.
You too.
Yeah.
Ah.
I got admission last year. So, 2023.
But why you? Yeah. Our study here began in 2023.
Yes.
Okay. I just my brain is but with numbers. That's why I'm going to mathematics.
Yeah, exactly. That's why we are in mathematics because we are bad at numbers.
Of course, you don't need to calculate. Right?
Yeah, that's the
it's a whole point. Yes. Awesome. Wait, I just didn't see you. I think there was like mandatory course in differential geometry.
Yeah, I skipped it. Yeah.
You did not like push.
Yeah. Differential geometry I studied in my previous master's degree in India. So it's so difficult for me, differential geometry and differential topology. Yeah.
Yes, and Pushkar, did you see his lectures?
No.
He's just reading I don't know how to say it, old Moscow style, like you're talking about some theorem, definition you have a theorem, and it's a problem for you.
Oh.
You need to prove that problem. Yeah, so something like that. Like you have to prove a lot of stuff to understand stuff.
Actually, you know what? That is a proper way to study mathematics. Like you know the theorem, now you have to apply the
Yeah,
theorem.
yeah, it makes sense. And his theorems are what the stuff that he give you as a problem is not complicated thing. So yeah, it's his style. So it's a way to learn.
So what courses do you have in this?
Boy, I have like functional analysis. It's structural physics.
Yeah.
But I have algebraic geometry. Well, in this moment. Yeah.
Like
Or good pronunciation.
right?
Yeah, you're right. I don't know pronunciation of her second name. And well, Toric varieties is here now. And machine learning.
Machine learning.
Of course.
That is pretty, interesting combination because at one point you were handling deep algebra and another point you were handling deep machine learning.
No, it's not deep. It's introductory, but I don't know. I just I need to some backup plan if I don't understand that I'm not good at mathematics.
Okay.
Like because
Yes, that is a very good choice. Like.
and it's I don't know. It's kind of interesting as well. Right?
Yeah.
So, and what course do you have?
I have category theory
Oh, wow.
by Pavlov, then cognitive algebra.
Oh, you're
Yeah. So after that I have symmetric functions like in Rupert. Then sister algebra and compact quantum groups.
Whoa, wow, awesome. Tchaikovsky's.
Yes, Tchaikovsky.
Основной. Like,
And this course.
wow, so you're like super algebraic dude. I don't know if it's algebraic.
Yeah, exactly. That's the whole point of coming here because I have seen that a lot of universities there are a lot of algebra professors.
Oh yeah, it's not the case in India.
It is in the case of India, but I thought that because of Professor Katrina America, I know her, my professors in India, they told me that you should go for her.
Wow, so popular.
Yeah.
Awesome. So it's really your scientific advisor?
My scientific audiences.
Gradient. Oh. So how is
Man, we are dealing with some, things which are going over my head. So difficult, man. This is called A-infinity algebra.
no. I heard something about this. Yeah, I heard like minutes over my head.
Yeah, man, A-infinity algebra. So basically, we are dealing with category theory and this other stuff, but still there are a lot of things to improve.
But at least you learn something.
Yeah, at least I'm trying to.
Some vowels. I thought thinking algebras is like topology stuff.
No, man, that's the thing. When I heard about infinity algebra, I thought that okay, it will be connected with topology. But now I am seeing that this is applied in physics.
There now, right? Oh my god.
Man.
Your physics is wild, okay?
Yeah.
Awesome.
Who is your?
Godunov.
Oh, Godunov. Yes, man. Last semester I attended Godunov's course. Cohomology theory.
Yeah. So I am doing some stuff that covers. I think it's about connection of algebraic geometry and quantum theory. My problem is now is you know what scheme is? You know what the scheme is?
Yeah.
Okay, no problem. The problem that I need to solve. Given a scheme good enough over complex numbers, good enough to have an notification. Like, you know what a notification? That's like it should locally be like how do you say it? Finite type, so it's locally just spectrum of polynomial factor of covering this trivialization. With spectrums are finite. So you can assume that it's kind of complex manifold when you're looking not on the spectrum but on the. I hope you. You just assume that it's complex manifold because local is just a C string of polynomials factored by some relation. You're just saying let's just assume that it's not like spectrums in this some weird topology, but a subspace of typical Cn, which is defined by this idea, like local, and it's kind of patched together. So it's a complex analytical space. It's not manifold, but
analytical space.
it's so so we have something like that. And the question: does there exist an affine scheme over C as well, with such that its analytification is chromatically equivalent to analytification of first scheme?
That's pretty interesting.
Yeah, I hope. I'm going close. I hope.
Hopefully,
So it's kind of like this affine transition from scheme to.
Yes. In the identification.
Yes.
That's pretty interesting.
Yes. So how do you not faculty? Do you like it?
Lot. Yeah.
True. Is it better than in India?
I personally like the environment. Like say outside of a classroom there are blackboards and stuff. So what happened? In the last semester, so I used to come here at 10 o'clock in the morning, and I used to go back to my dorm at 11 o'clock at night. So the whole day I was.
Oh wow! I'm not so big fan of this fact, but it's good. It's good.
Yeah, the whole whether I have class or not, I used to come here solving questions here and there.
Yeah, it's very good.
Yeah, it's very good. I like it.
So I actually, it's my second semester math faculty, and I like it as well. I graduated from Harvard.
Okay, so your background is not from HSC.
Yeah, not from
Okay.
It's not when mathematics, but.
Yeah, exactly. So you are you and I are in the same boat.
Okay. By the way, what don't you do?
In the 7th dormitory in School Street.
Damn, it's okay.
Where do you live?
It's Stockholm.
Oh man, that's so far.
Yeah. You know where it is.
Yeah, because there are a lot of guys from Pakistan, I think, in that Sebastopol dorm.
I never met them. I know there are guys from Bangladesh, Turkey, Ecuador, Peru, Mali, but I don't know anyone from Pakistan.
No, because I have met a lot of guys from various faculties, and they are all in Sebastopol dorm. So
Yes, also because I know 60% of foreign students.
man.
It's if you want, you can. We just wanted to order 2 1-liter pizzas.
Yeah.
So if you want, you can tomorrow.
Yeah, sure.
But it's okay. Some dang. And this is so. Where is Toric number 17? Is okay.
It's neon city. It's a purple line.
What?
Purple line, 7th line.
Oh. Sure. Yeah, first. What's number 17?
Not 77.
Sure. Thanks.
Yeah.
Oh, you have the gym.
Yeah, this one. This is the dorm. Because there are 2 buildings. This is the first building while they have 9 floors. And this is the second building. I live in this building.
Is it good building?
Yeah. And top of that, it is a good, but the charges are less.
Charges are less.
Yeah, like say for the first building, the 9th floor building.
Ah.
Yeah.
Okay.
So for the my point. Like when I tell people in my town that we have our own YouTube channel.
It's awesome, yes.
Yes, exactly.
But unfortunately, because of that, I'm just too lazy to go on the lecture, but
Yeah, exactly. When I say that we have blackboards outside the classroom and this and that stuff, they are like, oh.
I know it's so. I know Pokrovka building. Like,
Yes.
It's like huge, and this place is just literally a school.
Yeah, exactly. I hate
Very-
that building, that Kokosk building.
I don't.
Yeah, I don't like that building. Yeah.
Why it's
It feels, I mean, it doesn't taste my soup. I mean, it
Ah.
doesn't suit my taste. So, like here you can see that it is a proper school, like where you can learn things with concentration.
oh, okay.
Yeah.
And I studied at university where you don't have like system with elective courses, and I'm so like I really like this system. The elective courses in masters. By the way, what university did you study for?
There is institutes, a bunch of institutes called Indian Institute of Technology, IIT. So I used to study there in one of the schools. I mean, that is my previous master's degree.
So it's your second.
Yeah, this is my second master's degree.
So did you obtain your master's degree in mathematics as well, or it's
No, it was mathematics.
okay.
Yeah. I mean, like say, when professor is telling these stuff, I remember because a few of these things I read in my previous master's degree. Yeah, the thing, but yeah, the most important thing is the quality of research in HSC. It's very good. And also, I want to attend a course from mathematics because
Which one is it?
the algebraic geometry.
Okay.
Yeah.
Okay, I did not see you.
Yeah, I want to attend the class, but you know what? In the last semester, since I was new, so I couldn't ask professor to deliver the lecture in English. Okay. I thought, I thought that since in the coursework it was in Russian, so I can't ask her. But
Okay.
yeah. But
did what we put here, you can get something much more complicated. So today we use only finite groups. Okay. Let us construct a toric variety. take this. Now it is not necessarily integer,
Yes.
and we can take the exponent. 2pi.
Okay.
And so,
And yeah, and then because m prime acts as because for any u in m prime, um is integer, this will be the kernel.
yeah. Okay.
And okay, this action and what we want from it.
Yeah, but just this action, what is the algebra of regular functions if we take sigma prime in sigma check in m prime? It is just the algebra of the polynomials in two variables. Okay? And now if we act by this group, this is exactly the diagonal action. And now if we take all the functions invariant under this action, it will naturally correspond to the lattice M.
Can you write this?
Yeah. So M prime and N acts so N over N prime acts on N prime. Okay? No, last time we gave the criteria to be smooth.
Okay.
And now, if you know about normal smooth form,
What? Normal?
if you have two lattices, what is their quotient?
Hmm?
If you have a, suppose that we have any dimension greater than 2, okay? And if you have two lattices, do you know that, so we have n contains n prime. Do you know that you can always find the basis of E1, E1, etc., En here, such that the basis here will be, if it has the same rank, A1, E1, A2, E2, etc. And En.
Yeah. Can I give?
Yeah, yeah, sure. Я без микрофона пришла, ничего хорошего не будет даже если не. Вот, короче, есть нормальная форма измерения. Почему, когда идет решетка, то фактор, какой-то объемная группа, она в нашем случае конечная, она имеет такой вид. Но она будет иметь вид как бы z по a1, z по a2, тогда z по a. Внезапная волна.
Ну, это нормальная форма Смита, это правда. Окей.
Да.
Сейчас. А что мы хотим взять? Просто какую-то подрешетку на 4. Правильно?
Мы хотим, посмотрите, какая наша цель. Значит, вектор конус называется симплекциальным, если, грубо говоря, не порождающее, линейно независимое. Вот, пускай у нас есть, выделен симплекциальный конус полной размерности, мы хотим доказать, что соответствующее афиноэзотерическое многообразие получается примерно как здесь, из c в степени n по какому-то действию альберговой группы.
Какой у нас критерий был для гладкости? Разве не такой, что он должен быть специального полного размера? А, нет, полного
Вот
размера.
смотрите, полный размер мы не требовали. Мы требовали, чтобы этот набор векторов на ребрах порождающих дополнялся до базы всей решетки. То есть полный размер мы не требовали. Ну, просто чтобы там произведение над со звездой разрешить форму. Ну, то есть, да, тут вопрос, почему, если ребер ровно столько же, сколько размерность, почему оно все-таки более-менее хорошее? Количество многообразия не очень плохое.
Сейчас так. У нас в V4 есть какой-то базис, ну там А и Ж3, Е и Ж3. При условии того, что вот эти вот вещи, они линейно независимы, надо понять, почему их можно привести буквально к виду фактора
Давайте сначала скажем, где у нас кто. Вот у нас есть сигма, то есть сигма, симплекциальный конус в n, да? Кто такой n'? Вот вам дали симплекциальный конус в n.
Специально, еще раз, что значит?
Ну, грубо говоря, если это трехмерное пространство,
Ну вот сейчас мы как раз хотим сделать более-менее понять, потому что сейчас этого не видно. Вот если привести эту подрешетку вот по нормальной форме, потому что у нас есть нормальная форма свит, ее половик можно привести вот в форме А1, Д1, А2, Е2, А1, Е1.
Да, надо как-то так правильно написать. Вот, еще раз, вот под разбили, да? Сейчас мы не под разбили. Давайте я тут что-нибудь нарисуем. Вот здесь 2, да? А здесь 3 я выбираю. Раз. Вот.
проблема. Мне кажется, и на этом, в принципе, тоже можно посмотреть. Ну, на F' он должен быть C2. Как ни крути,
На H3. Сейчас. Я сама запуталась. Я хочу подумать, которая будет точно понятна. Еще раз, вот самая стандартная дурацкая картинка, да? Когда мы берем сигма, самый простой, неочевидный специальный конус. Мы берем раз диагональ, мы берем два диагональ, да? Это у нас получается сигма в Z2. Ну давайте разбираться, где у нас согласованные базисы. Значит, решетка имеет индекс 2. Что мы будем делать? Мы берем сейчас. Да, нам надо как-то написать порождающий, вы правы. Сейчас что-нибудь напишем. Еще раз. Значит, N' будет вот такая решетка. N' будет у нас вот она.
Да.
У нас N', да? Дальше, что получается? Какие у нас согласованные базисы? Надо взять вот этот вектор и вот этот вектор. Так?
Никого.
Чего?
Никого.
Для решеток N, N'. N это, значит, исходно же это целое, m' такое, что m будет неподвижной точкой.
Да.
То есть как бы решеткам дело нет до конуса.
Окей.
Просто вот у нас есть как нормальная форма Смита, и мы действуем. Вот эту координату мы умножаем на корень степени А1, на корень степени А2 и так далее.
Окей.
Да. Ну, хорошо. Значит, у нас был вот этот конус. Он, ну, вот сейчас у нас порождающие, которые являются базисом.
Да.
Вот. Соответственно, что? Мы же можем вот здесь взять действие, которое, значит, f1 не трогает, f2 умножает на минус единичку. Ну, точнее, оно соответствующее f2 умножается на минус единичку.
Как нам вот вообще действие, почему действие на n-штрих-то смотрим? Нам же действие на n-штрих надо.
Ну, смотри, нет, здесь надо на n'. Вот смотрите, у нас есть n содержит n',
Да.
и l' содержит m.
Да.
Нам нужно монома, соответствующее m' умножать окружная.
Да.
Вот у нас будет двойственный базис. То есть вот это будет конус m, который тоже как бы так выглядит. И у нас будет монома. Соответственно, мы как бы нечетные мономы будем не умножать на минус единичку, а мономы четной степени не будет. То есть по одной из переменных мономы нечетной степени мы на единичку умножаем, на минус единичку умножаем, другой нет. Вот. Ну все, как бы у нас есть действие на c2.
Да.
При этом действие на мономах степени 2 во второй переменной тривиальное.
Да.
Поэтому, когда мы будем рассматривать фактор по действию этой нашей z2, это то же самое, что для спектра инвариантов, алгебра инвариантов. Алгебра инвариантов порождена, соответственно, теми мономами, которые попали в M.
Да.
Все. Геометрический фактор совпадает с категорным, а категорный – это афинное торическое, соответствующее тому же конусу на решетке M.
Мы конус тут решили. Вот мы.
Ну, в смысле, он там где-то был.
Ну да, он где-то был.
Какая, как бы нам этого дела нету. Смотрите, у нас есть конечная группа.
Да.
Конус порожден какими-то f-ками, да?
Да.
Значит, в этой ситуации мы действуем группой z2, но при этом на порождающий конус мы это тоже можем написать.
Можно.
Ну как это действует?
Порождающий двойственного. Ну, порождающий двойственного конуса,
Да.
да.
Как бы, нам не важно как это действует. Мы напишем это действие, все.
Окей.
Как бы деталей нам не нужно.
После факторизации, ну вот у нас будет какое-то там.
Ну да, тут легко было сказать, что если есть конечная группа, значит фактор по действию конечной группы – это всегда геометрический фактор. Это, наверное, надо как-то пояснять, но это надолго. Вот. Ну то есть это на самом деле написано много где в книжках по теории инвариантов, например. Вот. Геометрический фактор – это значит слои являются орбитами. То есть как бы в одной.
Тогда факторы просто определяются так.
Сейчас. Факторы могут определяться хорошо, а могут плохо. Вот может быть какое-то действие в первой задаче, хотя непонятно, что такое фактор.
Вот там формально определение, вот берем вариант и все.
Ну, сейчас да. Сейчас это
Ну
такое.
это афинно
Ну,
только устроено.
когда хороший круг. Нет. Смотрите, действие, когда подгипергоны. Вот самый стандартный, например, проходит действие. X, Y. Вот как проходит TX, N+1Y. Как бы орбиты гиперболы, и непонятно, как бы, что с ними делать, вообще непонятно. Но это была группа со звездой действия. Вот.
Ну, конечные на афинно.
Конечные на фильм, все хорошо, да. То есть у нас орбиты бывают набора точек в количестве не больше, чем мощность G. По факту у нас тут будет большинство орбит G, у нуля будет орбита из одной точки состоять. Ну и, наверное, где-то будет промежуточная точка, где часть корней из единицы обратится, а часть нет.
диаграфии у нас это C от S. Ну, это спектр C от S. Но у нас на правде действительно есть C от M, как то вложено. Вы представили действие